Welcome to my Artificial Intelligence Economy channel. This video is long, but if you stay until the end, you may finally understand what artificial intelligence infrastructure really means. We look at our screens and see magic. We type a question, and the machine answers with the collected wisdom of humanity. We ask for art, and the machine paints. Because of this seamless interaction, we have fallen into a collective trance. We believe that artificial intelligence is formless, weightless, and infinite. We imagine it living in a metaphorical cloud, free from the hard constraints of the physical world. But this is a profound misunderstanding of what is actually happening right now. The truth is much heavier. Artificial intelligence is not virtual. It is the most material, resource-intensive, and physically constraining technology humanity has ever attempted to build. It is forged in steel, woven in copper, submerged in cooling liquids, and fed by massive rivers of electricity. What we call intelligence is currently being manufactured in brutal, industrial factories known as data centers. This is not just an industry analysis. This is a deep exploration of how infrastructure has become the new foundation of global power. We will uncover why tech giants are spending trillions without hesitation, whether this is a financial bubble or a necessary human evolution, and what it truly means when cognitive power becomes a tangible resource. Here is the core truth you must internalize before we begin. The future of human intelligence is not limited by the elegance of our algorithms. It is limited by electricity, materials, and hard infrastructure. The future belongs to whoever controls the physical grid. Chapter 1. The Illusion of Artificial Intelligence. Summary. We believe intelligence is virtual, but it is bound by cold steel, silicon, and enormous capital. When you interact with a large language model, you are not speaking to a ghost in the machine. You are sending a signal through a continent, triggering a physical reaction inside a heavily guarded facility. In these facilities, tens of thousands of processors burn hot, consuming massive amounts of power to calculate the next logical token. The public fascination with software hides the staggering reality of the hardware required to sustain it. Consider the horizon of ambition. In the United States, Open Artificial Intelligence, Microsoft, and others are collaborating on super data centers like the Stargate project, which carries a planned investment of $500 billion. To put that number into perspective, it is equivalent to the entire gross domestic product of a medium-sized nation. But even that staggering number is just the beginning of a much larger game. We are witnessing a shift from conceptual science to heavy industry. The company Open Artificial Intelligence recently restructured its corporate architecture to pave the way for an initial public offering, with an ultimate vision of funneling $1.4 trillion into infrastructure development. They recognize that the current evolution of machine learning is no longer a matter of code refinement. It is a brutal, physics-based war of attrition. Why does it require such an astronomical investment? Because intelligence in the era of deep learning is quantifiable. It is directly proportional to the number of parameters a model contains and the amount of compute power thrown at it. Every time a model upgrades, from one generation to the next, the compute requirement grows by 10 to 100 times. This relentless scaling turns the pursuit of truth into a pure competition of physical resources. Chapter 2. Compute is the new resource. Summary. In the age of algorithms, processing power replaces oil as the ultimate global currency. For over a century, geopolitical power was defined by whoever controlled the flow of hydrocarbons. Oil powered the engines of the Industrial Revolution. Today, we are transitioning into an era where compute power is the new oil. Compute is the foundational fuel that will drive the automation of human knowledge, reasoning, and creativity. It is the resource that will dictate which corporations survive and which nations maintain their dominance. Cloud providers and tech titans understand this shift perfectly. They treat compute as their strategic land reserve for the digital age. For example, Amazon is projected to increase its capital expenditures to $200 billion by the year 2026. These massive allocations are driven by pure market dynamics and the unprecedented demand for artificial intelligence leases. This insatiable hunger exists because leading companies cannot afford to stagnate in the race to achieve artificial general intelligence. Being second means irrelevance. If one company reaches the next breakthrough first, they could systematically dismantle existing search, social media, and advertising paradigms overnight. Therefore, securing compute is not just an operational expense. It is an absolute prerequisite for corporate survival. The demand originates from two distinct phases. The first is the training phase, where massive clusters of processors spend months absorbing human knowledge to build trillions of logical parameters. The second is the inference phase, where the educated model answers questions for billions of users across the globe. Currently, the industry agrees that inference will ultimately dominate the infrastructure load, transforming the data center into a continuous intelligence factory. Chapter 3. Inside the data center. Summary. Behind the seamless interface lies a brutal architecture of chips, optical modules, and copper spines. To truly understand the scale of this revolution, we must peel back the metal skin of a server cabinet. Inside a traditional high-end artificial intelligence server, you will find extremely expensive components working in unison. 8 core graphics processing units are embedded alongside high-bandwidth memory chips, bound together by advanced packaging technologies. The processors are only a fraction of the equation. When you connect tens of thousands of processors together, the bottleneck quickly becomes communication. Data must travel between chips without delay. This macro network requires a labyrinth of switches, fiber optic cables, and optical modules. These optical modules translate electrical signals into light, firing information across the facility. Optical modules represent a massive growth sector, with the year 2026 marking the commercialization boom for 1.6 terabit speeds. As the models grow, the physical limits of traditional networking fail. This brings us to the newest iterations of hardware, where the very architecture of the cabinet is reimagined. Inside advanced configurations like the NVL72, traditional boundaries are destroyed. To maximize speed, the system utilizes a massive copper spine, weighing nearly 70 pounds, connecting 72 processors so intimately that they function as a single, unified brain. But with great density comes unimaginable heat. A single modern cabinet can draw upwards of 120 kilowatts of power. At this level of energy consumption, traditional air cooling is completely obsolete. If you attempted to cool this density with air, the chips would melt into slag. Liquid cooling has transitioned from a niche luxury to an absolute necessity, dictating the physical layout of future data centers. Chapter 4. The infrastructure explosion. Summary. Capital is pouring trillions into facilities just to stay alive in the next technological era. The speed at which these megastructures are being assembled defies traditional economic logic. Consider the financial projections for the tech giants. In 2025, the top 5 North American tech titans are expected to spend $410 billion on capital expenditures. By 2026, that staggering number is projected to swell to $690 billion. Where is all this money flowing? It flows directly into the pockets of the infrastructure suppliers. The companies that manufacture the processors, the printed circuit boards, the liquid cooling manifolds, and the optical transceivers are experiencing unprecedented revenue growth. For instance, co-packaged optics, a technology that integrates optical engines directly with the silicon to shorten data paths and reduce power, will see major commercial deployment by 2026. The industry is undergoing a structural upgrade forced by the speed of processor evolution. Every time a faster chip is released, the entire surrounding ecosystem must be forcibly upgraded to keep pace. If a new graphics processing unit doubles its data throughput, the optical modules must bite the bullet and upgrade from 800 gigabits to 1.6 terabits. This dynamic creates a ruthless environment for suppliers. They face only two possible outcomes. They must either evolve their technological capabilities in perfect synchronization with the leading chip designers, or they will be instantly kicked off the poker table. The subsectors of artificial intelligence infrastructure are not speculative concepts. They are the irreplaceable physical foundation making commercialization possible. Chapter 5. The Race for Power. Summary: electricity has become the ultimate bottleneck, dictating who can build the future and who will fade. While silicon and copper can be manufactured, there is one resource that cannot be simply printed with capital. That resource is electricity. The hardest limit on the expansion of human intelligence is now the electrical grid. The industry has reached a point where manufacturers can readily supply the silicon processors, but the tech companies simply do not have the electricity required to turn them on. The numbers reveal a looming energy crisis. In the United States, the power grid has barely grown over the past 2 decades, expanding at less than 1% per year. Meanwhile, the demands of artificial intelligence data centers are exploding. Open Artificial Intelligence pointed out to the White House that China added 429 gigawatts of power in 2024, while America only added 51 gigawatts. To feed a supercluster of processors, companies must find massive blocks of continuous power. A planned target of 10 gigawatts for a single data center project represents a substantial percentage of a major city's overall capability. Because traditional power companies move too slowly, tech giants are being forced to source their own energy. They are sweeping up small gas turbines and exploring nuclear solutions just to keep the machines running. This scarcity forces radical innovation in power delivery. To minimize energy loss during transmission within the data center, the industry is pushing towards high-voltage direct current systems. Transitioning to 800-volt architectures allows facilities to greatly reduce the astonishing amount of copper wiring required, saving resources while squeezing every last drop of efficiency out of the precious power supply. Chapter 6. The Economics of Overinvestment. Summary: companies invest billions not from confidence but from the absolute terror of being left behind. When observers look at the trillions being pledged to data centers, they naturally question if we are witnessing a historic bubble. But the leaders of these tech empires are operating under a specific psychological and strategic framework. Their driving philosophy is simple but brutal. Underinvestment is infinitely riskier than overinvestment. Let us analyze the psychology of this dilemma. If a corporation overbuilds its data centers, what is the worst-case scenario? They are left with highly valuable physical assets. They have real estate, power contracts, and computing hardware. If artificial intelligence demand softens, they can repurpose this compute for internal efficiency or lease it to smaller entities. The downside is a manageable financial loss. However, the risk of underinvestment is fatal. If a tech giant fails to secure enough infrastructure and a competitor achieves a massive breakthrough in artificial general intelligence, the cautious company will be instantly obsoleted. No chief executive officer wants to become the next Nokia. They would rather face the wrath of Wall Street over bloated budgets than suffer total annihilation in the market. This fear drives a herd mentality that manifests as physical steel and concrete. Companies are hoarding compute the way nations hoard weapons during a Cold War. It is a classic prisoner's dilemma. You must buy the processors because you know your rivals are buying them. If you wait 2 years to see how the market evolves, you will not even have a ticket to enter the arena. Chapter 7. The bottleneck of reality. Summary. The expansion of the mind meets the hard limits of physical space and thermodynamics. The friction between digital ambition and physical reality has never been more pronounced. We speak of training models on trillions of words, sifting through the sum total of human culture in mere months. But doing so requires operating vast clusters consisting of hundreds of thousands of processors. At this scale, the laws of physics become the primary enemy. Consider the logistics of maintaining such an array. Even with a minimal failure rate of 1% per week, a cluster of 100,000 chips would result in 1,000 hardware failures. That means unimaginable tonnage of hardware must be physically removed, transported, and replaced continuously. The logistics require fleets of cargo trucks just to handle the defective components. Furthermore, the manufacturing supply chain is strained at every conceivable node. It is not just the cutting-edge processors that are lacking. The world lacks high-bandwidth memory chips, advanced packaging capacity, and crucially, electrical transformers. Transformers are built with specialized grain-oriented electrical steel, and the wait times for these essential grid components have stretched from 3 months to over 18 months. This represents the ultimate paradox of artificial intelligence. We are attempting to build a mind that operates at the speed of light, but we are held back by the time it takes to smelt steel, wind copper, and pour concrete. The limit of human imagination is now dictated by the ponderous and unforgiving speed of heavy industrial manufacturing. Chapter 8. The rewriting of industrial order. Summary. A new monopoly rises while an alliance of titans fights to reclaim control over the infrastructure. The unprecedented capital being poured into artificial intelligence has completely rewritten the hierarchy of the technology industry. In the past, cloud providers held the supreme power, dictating terms to component suppliers. Today, because one company produces the only processors capable of handling these demands, the balance of power has inverted. The chip designer now sets the standards for the entire system. When a cloud giant spends billions on a supercluster, they are forced to accept a proprietary ecosystem. They must buy the interconnects, the networking protocols, and the exact architectural standards dictated by the chip monopoly. This dynamic squeezes the profit margins of the cloud providers and places the fundamental control of the industry into very few hands. But where there is oppression, there is rebellion. The tech giants are not remaining passive. They have formed coalitions, often referred to as an Avenger Alliance, to break the monopoly. Companies like Microsoft, Meta, and Advanced Micro Devices are pushing open-source communication protocols. Their goal is to create a standardized infrastructure where chips from different manufacturers can talk to each other freely. Simultaneously, the cloud giants are pouring billions into developing their own custom silicon. These application-specific integrated circuits strip away the general functionality of traditional processors and focus exclusively on artificial intelligence matrix multiplication. By using in-house chips for inference tasks, they hope to slowly reclaim their independence and protect their long-term profitability. Chapter 9. Who owns the future? Summary. The victor will not be the one with the best algorithm, but the one who controls the physical grid. As we stand on the edge of this unprecedented economic shift, we must reevaluate what we consider valuable. The narrative surrounding artificial intelligence has focused entirely on software capabilities. We argue over hallucinations, ethics, and linguistic nuance. But these debates hover above the harsh reality of the trenches. The real war is being fought over substations, cooling patents, and megawatt allocations. The trillions of dollars being mobilized today will leave a permanent mark on the planet. Even if the financial returns of artificial intelligence applications fall short of the exalted expectations, the infrastructure will remain. We are currently laying down the nervous system of the next century. Just as the railway boom connected continents long after the financial panic subsided, the data centers of today will become the enduring bedrock of tomorrow. We must accept that intelligence is no longer an intangible concept native only to biological minds. Intelligence has been successfully commoditized. It can be measured, bottled, and sold like electricity. And like any commodity, its value will be dictated by supply chains, geopolitics, and massive industrial processing facilities. If intelligence becomes a resource, then the ultimate question is not who will write the most elegant code. The question is not who will design the most clever neural network. The profound question we must all face as we enter this brave new world is this: when cognitive power is driven entirely by infrastructure, who will ultimately control the switch?